Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already done so, hit the pause button and click the subscribe button right now. For the last dozen videos, if you have been following my videos, you know that we were looking at generative adversarial networks. We looked at various applications, whether it is cycle GANs or pix-to-pix and many other applications. Now I'm switching gears, starting this video, and I'm going to talk about anomaly detection, especially in images. Why am I doing this? Because this is one of the most common requests I get from the viewers of my channel. And I'm not gonna, at least I don't anticipate to make many videos on this topic. I'm just going to make 3 or 4 videos. The first one here to show you how we can actually train a model using a whole bunch of normal images, and then anything that's normal is an anomaly. Remember, if you have good and bad images and you want to design a binary classifier, you'll get much better accuracy that way because you have images for both good and bad. But what if you have a whole bunch of good or normal images and you want to design a way of defining anything that's not normal as abnormal or anomaly? That's exactly what we're going to do here. Okay, and we're going to use autoencoders, and if you have watched my previous autoencoder videos, you know that, okay, we are going to look at reconstruction error and then say, okay, if this reconstruction error is larger than certain threshold, then that is an anomaly. That's exactly what we're going to do. In addition to that, I'm going to throw in additional metric to guide us into finding anomalies, which is kernel density estimation, and I'll talk about that in a minute. In the next couple of videos, I will focus a bit on, okay, we know that, okay, we can find out what an anomaly is, but why is that an anomaly? Can you show me the regions where you see higher probability of that not being a normal image or so? So for that, I'm not planning on using autoencoders. I'll just use a regular convolutional neural network, and let's wait for that video for the next week. But for now, let's go ahead and focus on our identifying anomaly images. So the plan here is, you know convolutional neural network. I hope you do know what convolutional neural network is and what an autoencoder is. So here I'm just showing you a VGG16 architecture where you go from a couple of convolutional layers. We call that a block of convolution, another block, another block, another block, another block, and then you have the fully connected layers, and the output is going to be 1000 different probabilities, each for a different class. For autoencoder, we are going to chop this somewhere in the middle, and we are going to almost put a mirror reflection of what you have here. So the left-hand side here is called the encoder because we are taking a large image and encoding that into a very small vector. In this example, the vector is 7 by 7 by 7. Well, hey, I just reversed this. That's why it looks a bit weird. But in this example, this is 7 by 7 by 7. It can be, I don't know, 2 by 2 by 4, whatever that smallish size is. This is the encoded vector. Now, we go from that small vector, or a tensor in this example, we go from that small tensor, and then we gradually upscale the image and go back all the way to our original image size to reconstruct our image back. And this is basically what an autoencoder is. So the first part is the encoder, and the second part is the decoder. So we supply an input image and you reconstruct an input image back. Now, what good is that? All we're proving is, yeah, we can take an input and then we can reconstruct that input. So this is exactly what we are going to leverage for our anomaly detection. Because what if we cannot reconstruct the original image up to like 100%? In fact, we cannot achieve 100%, right? So what if we can get 95% there? What if the reconstruction error is like above or below 90%? Reconstruction accuracy is below 90%. So that's where we can set a threshold and say, okay, that is an anomaly. So here, there is an image with some parasite right in there, and then when you go, it goes through this, and this is an actual reconstruction of this image, and you can see that parasite is not very evident, not very clear after reconstruction. So there must be some reconstruction error associated with this because we are comparing the output image against the input image, and we say, hey, this is not the same. So you look at the mean squared error and you say, okay, this is not the same. So large reconstruction error means this image is an anomaly. So this is the idea, but is reconstruction error enough to spot anomaly in images, it completely depends upon your image. Sometimes it's enough. Sometimes you have a whole bunch of cat images and then you supply a dog image and it's like, hey, this doesn't look like a cat, and then this is an anomaly, right? So those in those examples, it may actually work out. But there is a paper from 2019 called Robust Anomaly Detection in Images Using Adversarial Autoencoders. Basically, what they proposed is, hey, look at the latent space, and maybe we can benefit from the latent representation. And the summary of this is the approach that we're going to take is also look at the likelihood of an image in the latent space of good images. So once you have this latent space of good images, now we are going to say, okay, how far is my new image, let's say the anomaly image, from this latent space? If it is far enough, then that's an anomaly. If it is very close by, then it's not an anomaly. Again, we have to set another threshold right there. So there is one threshold for this latent space, another threshold for our reconstruction error, and we can use these two metrics and say, okay, if either of these holds good, then it's an anomaly. Now, what about this latent space? I don't want to make things too complicated, so let's go ahead and simplify this latent space discussion. If you only look at the encoder part, where does it end? It ends at this bottleneck, right? And we said in this architecture that I'm showing you on the screen, the bottleneck has a size of 7 by 7 by 7. So we send an image through, and then what you get is a tensor of 7 by 7 by 7. So we are going to use a kernel density estimation to calculate the likelihood of an image belonging to this normal or good class. So what does that mean? Well, KDE for training data provides an estimate. KDE is just basically gives an estimate of, okay, how of your probability distribution, and if a data point is close to that distribution or not. So density estimation, again, please look into what kernel density estimation is and how it works and all that. This is not a tutorial about it, but we are going to use that as a metric. So for the training data, it provides an estimate of where the input vector space lies, right? So we feed this with, let's say, 1,000 different normal, neutral, or good images. And now you map out your kernel density estimation. And then you say, okay, I understand this space. And then once you do that, then you put your anomaly image or any other image and then estimate your KDE and then see, is that really close by or is that far away? So basically here, the key assumption we are making is that the anomaly images have densities that are farther away from the densities of the training images. So this latent space, we're just going to use that 7 by 7 by 7. So this would be 7 times 7 times 7, that much vector. And we're going to take that vector and get a kernel density estimate, and then use that kernel density estimate as our gold standard. And then any other image, where does it lie within this KDE? That's pretty much it. Okay, and of course, we are going to work with the most compressed feature map. Why are we getting this at 7 by 7 by 7 and why not here? That's because we want to minimize the dimensionality. If you have a very humongous dimensionality, then you have like this big of a sphere for our volume, let's say, for your normal images, and your anomalies may be within that. We want to minimize the the dimensionality to make sure that we get a very nice tight distribution for your KDE, and then we can actually compare our new image KDE against this tight requirements or restrictions. So that's the reason why we want to work with most compressed feature map. And to identify anomalies, like I just mentioned, we set the threshold on this KDE and also on the reconstruction error. So, and how do we choose this threshold values? Well, basically, you just send a whole bunch of normal images through this and then find out exactly what density distribution looks like and how the reconstruction errors look like, and then say, okay, so this is my density threshold and this is your reconstruction threshold. It also helps if you have a whole bunch of anomaly images, so you get an idea of what typical anomalies are going to give you in terms of your density and also reconstruction errors. So that's pretty much it. And now let's go ahead and jump into the code and get this thing going in Keras. Okay, so here is our code, and the data set that I'm going to use, you can use any anomaly data set. I keep working with the same data set here. As you probably know, this is a malarial. Again, you can get the data set from here. I'll share the code. You can download this data. So basically, if you're wondering what the data set actually has, it's got two folders, uninfected and parasited, of my cell images right there. Yeah. So as you can see, they're all clean images. So these are all what I consider normal. What I don't consider as normal is this parasited. As you will see in a second, they seem to have some parasites in them, and this is what I'm calling anomaly. In reality, this problem is better approached as a binary classification, which I have already done in the past, but right now I'm trying to see if anomaly detection can actually detect my parasited images as anomalies. That's it. You can take any of the other anomaly data sets, like I said, whatever I'm showing you and the code that I'm going to share, it doesn't care what images you have. You can resize to whatever size you want, and you can go ahead and work on your data sets. Just a quick note. Okay, now let's jump in. I have already trained this model, so I don't waste your time, but let me go through this line by line. We are not going to use anything that is tricky from a training point of view. So we are going to use from Keras, we are going to use sequential, convolutional 2D, max pooling, upsampling, and also I'm using image data generator. I have only a few images, but yeah, let's go ahead and use image data generator to just load a batch of images at a time. And the reason I'm using image data generator and not just loading everything in the memory is I don't know what type of data sets you have. You probably have a million images, and you don't want to load all of those in memory, right? So that's why this code should be able to work on your data sets, hopefully. Okay, we are going to read images using Pillow library and plot using matplotlib, numpy, and random, so we can pick random images for testing and training purposes. Okay, and I am going to set the size of my images to 128 by 128 and a batch size of 64 at a time. Now I'm defining my data generator. Again, if you don't know what I'm talking about, then you should go back to data augmentation video that I have done in the past and then understand what data generator is. So I'm defining my data gen, nothing fancy. We're not doing any transformations like no rotations, flipping, and all that kind of stuff. You can augment your data many ways. The reason I'm using this, the only thing that I'm using here is to rescale my input data by dividing it by 255. To squeeze all the pixel values to between 0 and 1. Otherwise, they're between 0 and 255. That's the only thing that I'm doing here. Otherwise, I defined 3 generators, one for training, one for validation, and one for anomaly. By the way, when you download that data set, you only get 2 folders, one for uninfected, one for parasited. I just copied a few of the uninfected ones and put them into test, like about 75, I believe. Yeah, 75 of these images, put them in test. So I can just use them for validation during the training process and also after the training. That's it. Okay, so my train generator, it's flowing from directory from my uninfected train, and I'm resizing them to 128 by 128. And a batch size of 64, and my class mode, it's not a multi-class, it's just a class mode of input, so it's just giving me those images when I'm calling the generator. Same with validation, same with anomaly. The only thing different between these 3 is where the images are coming from. That's it. Okay, so I did run all of these and then put together a model. This is completely up to you. An autoencoder goes from a large size to a smaller size and then back to a large size, right, in terms of your image size. So you can start with 64 filters, and you can go up in filters, or you can go down in filters. It's completely up to you. Do not confuse the number of filters with your image size. The image size is going down because you have a max pooling right there. You can change your max pooling to 4x4 if you want. I'm using 2x2, so they go gradually down in size. And then I'm doing upsampling right there, and we are very symmetric, right? So here max pooling, upsampling, think of it as kind of opposite to max pooling. And then symmetrically going back up in terms of number of filters. And the final layer is giving me 3 channels because our input images are RGB. 3 channels. I want 3 channels as output. And we are applying a sigmoid, and we are compiling it using mean squared error. Again, we are trying to compare our output image or reconstructed image with our input image. So mean square error is a great metric to do that. So when you do that and when you print out the summary, you can actually see that, okay, we started off with 128 by 128 by 3, and the next layer is 64, and gradually it goes down. So the bottleneck layer here is 16 by 16 by 16. In my presentation, I showed you 7 by 7 by 7. So this is 16 by 16 by 16. If you want, you can actually add another convolution layer with a different, let's say 8 filters, and then 2 by 2, and then even go down further to 8 by 8 or so. But this is what I chose, and that's it. This is very straightforward and very simple. And then now I am going to model.fit my train generator, and I trained for 1000 epochs. And do I have my plot? If not, I can go ahead and plot this one more time so you have a quick look at how the training went. So it did go pretty well, as you can see. After 200 epochs, it kind of, the return is pretty slow, but anyway, it seems to be saturated right there. So I'm confident about my training, which means when I reconstruct my images, I should actually get a pretty decent reconstruction. Let's go ahead and test that out. How do we do that? Well, let's actually get a batch of images because we defined our generator. And how do you generate a batch of images? You just do .next right there. Yeah. So here I'm actually getting all the batches by capturing it right here. So what at the end of this, let's see. At the end of this, you should see a data underscore batch right there, which shows me 6 different batches because I have 500 images, and each batch is 64. So after the first 5, I only have 52 images left over. So my last batch has 52. So this is all of my images captured right here. Okay. And of those, I'm just picking the first batch and then just doing the predictions. And now I'm going to go ahead and predict on some random images just to see how the reconstruction looks like. Again, this is a sanity check that you have to do. And let's go ahead and look at this. So let's run one more time. Yeah, there you go. I don't know what the previous one was, but here you can see this is the input, and that's the corresponding reconstructed output. Looks very good, actually. I'm surprised how good the reconstruction is. I picked the same image. It's not a good reconstruction, right? So let's do, that's a pretty good reconstruction. That's a pretty good reconstruction. So it can be better. You see how this is different. So the reconstruction error on this image would be a bit high. Yeah, the reconstruction. Yeah, I'm not sure what's going on with this image, but let's say the reconstruction is, I'm curious if I'm plotting the same one. I think, yeah, I am. Let's not worry about this too much, but let's continue. But on average, it's actually doing a decent job in terms of reconstruction. Now, if you would like to check the error between your validation data, right, which is nothing but your normal images, and the anomaly data, let's go ahead and model.evaluate. What do you get when you evaluate? You get your accuracy values, right? So let's go ahead and do validation. So we are basically checking the reconstruction error for validation data and reconstruction error for my anomaly data. Yeah, because our anomaly data, it's fetching images from my anomaly generator. So am I printing it? Yeah. So let's go ahead and print the reconstruction error here. So the reconstruction error for validation data is 0.30. By the way, when you do model.evaluate, it's going to return you 2 things. I hope you know that. The 2 things are whatever we define in our model during the training process. Loss and metrics. If you have multiple metrics, it returns you multiple metrics. So in this case, both values are the same, 0.30888 and 0.30. That's because we are using same mean squared error as a metric and also as a loss function. That's why you're getting 2 of these. I hope you know that, again, basics, but it's important for us to understand that. Okay, so anomaly, sorry about that. Okay, so the reconstruction error for validation data is 0.309. The reconstruction for anomaly data is 0.2017. So there is some difference between anomaly data and the validation or the normal data. So that's a good sign. Now, to get our kernel density, I said we have to take our model up to the encoder part, right up to the end of the encoder part where we have the bottleneck. In our case, that was, if you go back and look at the model summary, up to the point where we get to this step 16, 16, 16. Okay, so let's go ahead and chop the model up to this point. There are many ways you can do that. You can load the original model and you can say, okay, give me only the layers up to this point, and then you can load the weights from that model and apply it to this. Here I am defining this as a new model with pretty much exactly the same thing. I call this encoder model. Exactly pretty much the same thing, except here when I slide to the right, I say get weights from my model.layers 0, model.layers 2, model.layers 4, right? So layer 2 is that one, layer 4 is the next one. So this is exact. So it populates this with the weights from the model that we just trained, which we called it model. So basically, I'm just taking this part and gave it a different name and getting the weights from already trained model. So far, so good. Why am I doing that? When I do my encoder model summary, you can see that I'm going all the way down to 16 by 16 by 16. And they already have weights. So I'm not going to train it. I'm just going to use that as my feature generator, or my latent vector generator, I should say. So that's the intention of using this. And now let's go ahead and use that to generate latent vector. How do you do that? All you need to do is encoder model.predict, right? On what? On my trained data set. And once you predict that, now you have the latent vectors that you can use to get kernel density. How do you get kernel density? Scikit-learn has the kernel density right there. So go ahead and import this from scikit-learn. And my encoded images, I've already done that. Where is my encoded images? Encoded images right there. I have 500 images. And as you can see here, the dimensions are 16 by 16 by 16. So we have this tensor, or the latent vector. I hate to call it vector because it's not a vector. We are going to flatten it in a minute. Then it is a vector. Until that point, it's my latent tensor. And I have 500 of them corresponding to each image in my training data set. Now that I have my encoded images, I want to convert that into a vector, like I just mentioned, flatten it, or get a vector so you can apply kernel density on it. This only works on 1D data. So how do I do that? So first of all, I got my encoder output shape, which is nothing but 16 by 16 by 16. And then all I'm just saying is output vector shape is just multiply 16, 16, 16. That's my output vector shape, which is nothing but, what is 16 times 16 times 16? Output vector shape, that's 4096, right? And now all I'm doing is, okay, go ahead and reshape my image into that shape for not image. I mean, go ahead and reshape my encoded image. I should have just called this encoded image, but this is just a list comprehension right there. So for each encoded image in my encoded images, go ahead and convert that into a vector and return that. That's exactly what happens here. Encoded image vector, encoded image vector. So I have 500 of these. Let's go ahead and open. I have 500 of these vectors. We're getting there. So once you have that, now we just need to calculate kernel density estimation. So right there, I'm applying that onto my encoded image vector. Okay, now we have KDE that's ready to be used on to my data set. So we fit a KDE right there. So now, first thing first, to set a threshold on our density and also on our reconstruction error, first we need to know what these values are on our normal images. To do that, I have a function right here, calculate the density and recon error. So in these lists, I'm going to capture these two parameters for all of my images. So what am I going to do? Load each image, okay? And then go ahead and predict using my encoder. What does that do? It gives you the latent tensor that we go ahead and reshape it into a vector so we can apply our KDE onto that, okay? And then reconstruction. I mean, now we have KDE, now we have density, now we need reconstruction error. So our reconstruction is basically your model.predict. which reconstructs your image. Now go ahead and look at reconstruction error using model.evaluate. It gives you two values. Go ahead and pick only the first one because we're using loss, or and also for metric we are using mean squared error. So now go ahead and add it to our density list and recon error list. And basically what I'm trying to do here is I create a list of all of these and then find the average of all these values and also the standard deviation of all of those. So at the end of this, it's going to return average density, standard deviation, average recon error, and standard deviation in the reconstruction error. And I apply that on what? On my training and anomaly data. So here I'm using the generator again to generate a batch of training images and a batch of anomaly images, and then just go ahead and use those as inputs to calculate my density and recon error from this function, and that's what captured in these two. So if I open uninfected values, so let's go ahead and open the uninfected values right there. We should have 4 of them, right? So the first one is average density. The next one is standard deviation in the density for all of these images combined. The next one here is our average reconstruction error. And this one is the average sigma or standard deviation in the reconstruction error. This is for my uninfected. So for the anomaly ones, I have anomaly values right there, and you can compare those. And the anomaly values are jumping all over the place. I mean, these images, I don't like to use them for anomaly detection, although I'm using them for anomaly detection, because there is a lot of dark area around it. The best way is, okay, you have the entire image filled with something, let's say a fabric that looks good, and then another image where you have fabric, but with some sort of anomalies in there. Yeah. Those are the ones where you get like the best anomaly detection for, using this approach. Anyway, so here you can see that my anomaly values mean is minus 1,769, but then the standard deviation is almost 5,000. So this is going to overlap with whatever the window we are going to set. That's why having 2 windows can be very useful. Not 2 windows, 2 parameters can be very useful. So this is a bit straightforward. So the reconstruction error for uninfected or my normal images is 0.016, and here it's 0.03. So this is about 2.5 times bigger than my uninfected. So maybe this is also another good metric here. So you have 2 metrics, like I already mentioned, and let's go ahead and use them. So that's exactly what I have done down here. There is a function called check anomaly, and it basically checks, sorry about this. It basically checks anomalies right there. What does it do? I set a density threshold of 2500 based on what I just saw. I set a reconstruction error of 0.304 based on what we just saw over there. And all it's doing is opening an image, converting that into a size 128 by 128. And I'm also showing it, so when we run this, we can see what the image looks like. And I'm normalizing or scaling the image by dividing it by 255 and adding an axis, so it is in the right format for our input. And then model.predict, you get your encoded image, but more importantly, we reshape this, or we convert that into a vector, so you get our density value. Same thing with reconstruction, model.predict, and once you do that, you can do the evaluation, and that gives you the reconstruction error. And basically down here, if my density is less than the threshold, or if my reconstruction error is greater than the error threshold, then it's an anomaly. Otherwise, it's not an anomaly. That's it. Okay, so finally, it's the moment of truth. So I am capturing all the file names from my anomaly data and also from my normal data. Why? Now I'm loading a random image from here and then supplying that as an input to this function, so we can check how well our anomaly detector is performing. So let's go ahead and do that, and let's plot it. So there is something here. It says this is an anomaly. Obviously, we are working with anomaly data, so we know that it is an anomaly. Oh, it says this is not an anomaly, even though so this is when I go back and play with my threshold values right there, or train it a bit further, or come up with a different model that actually works even better than what I have. So let's go ahead and check this on a couple of things. It says this is an anomaly. Obviously it is an anomaly. This is an anomaly. Let's do one more. This is not an anomaly. So I think some of the faint, this is obviously not an anomaly. This is, I mean, you can see this is an anomaly. Now let's check the same for a few normal images. So hopefully it should say this is not an anomaly. So it says this is an anomaly. So this is exactly when I'll go back and I have to adjust the parameters. Let's go ahead and check this on a couple of images. I have a feeling if the shape is not round enough, it's telling us that this is an anomaly, because if you remember, when we do the reconstruction, the reconstructed images appear to be more roundish than normal. That's exactly why this is, again, probably not a great data set to show this, but unfortunately this is the only one I have. Again, this is not an anomaly, so we're getting more not an anomalies than an anomaly, so I'm kind of happy with this. Again, like I said, the key lies, how do you make this model even more robust? First of all, this is where it all comes down to. Make sure your encoder and decoder, this is working fine. I am tempted to add another convolution layer with 8 of these filters right there and bring the size down even further. Maybe my latent space is too big. I want to bring that to even smaller. So come down to, right now we are doing 16 by 16 by 16. Maybe I'll come down to 8 by 8 by 8 or even 4 by 4 by 4. And then see how that works out. So this is what, again, how to modify that. That's one thing. The other thing, once you perfected that part, the next thing that you have to focus on is getting this density threshold and also your reconstruction threshold. Once you fine tune that, then I think you'll be good. Remember, I mean, we have 2 different metrics, 2 different parameters here. If you only have reconstruction error, it also works fine. But how good is it? This is the whole point of this, of adding our density as another metric to this. If you want, you can plot out the density values for your normal images and also the anomalies, and then visually set a threshold. Probably I should have done that, but I like to look at numbers. That's why I printed out the values, the average and standard deviation, so I can kind of space things out a bit easy looking at these numbers. Okay, so this is anomaly detection, and again, if for those of you who watched my Autoencoder videos that I have done a long time ago, if you still remember them, this should be pretty straightforward for you. All we are doing is just using a standard autoencoder approach, looking at reconstruction error. In addition to that, we also are playing with our bottleneck vector, and we call it latent tensor, and basically calculating the kernel distribution from this latent vector and just setting a threshold. You can find other tricks, other metrics by using these tensors. And if you have a better trick, please let others know by giving your response in the comments down below. Okay, if you really like this, again, do not forget to hit the like button. And of course, as usual, I request you to subscribe to this channel and wait for the next tutorial. Thank you, guys.